Yeah, thank you. Thank you very much for the invitation. It's my great pleasure to come all the way to here and then to give my talk. Yes, and I'm very happy with this. So, I guess this is my first time to give a talk in kind of a physics seminar. So I don't know how I should. Yeah. So I so as I think the I received a guidance saying that I should be more specific and make it clear that what I'm going to do in the very beginning of my talk. So let me make it very explicit and basic. And so the object the object that I'm going to study is some length in S3 or S1 cross D2 up to smooth isotropy. And then the theory that I want to talk about is Khovanov homology. So in the case of S3, it is Khovanov homology. In the case of S1 cross D2, it will be annular Khovanov homology. Annular. So there are some link invariants up to smooth isotropy. And then the goal of my talk is to explain that so there are many ways to define Khovanov homology. And in combinatoric model, when the link is too periodic or strongly invertible, then there exists a spectral sequence from relating Khovanov homology of the knot and the annular Khovanov homology of quotient. I will explain in more details in the middle of my talk. And the goal is explain the symplectic origin. And in the symplectic world, it is very obvious, very geometric. That's why this spectral sequence exists, which is very easy to see. What is two periodic? Two periodic means that there is a Z2 symmetry preserving the knot. There's a Z2 symmetry of the space which preserves the knot and act freely. And strongly invertible means that the knot will have two fixed points. So I will explain more in details. So why? So some background. So links in R3, link in S3 is the theory is the same in links in R3. And then what people do is what Khovanov did is you can project a link. So from link projection, something like this, you project a link to R2. Khovanov. You map it to by greater chain complexes. Huh? Okay. And then maybe I should be more careful with my writing. So if if the nodes are inside a disk, if they are of this form, inside a disk, and outside the same, then so this is from a node projection to migrated chain compress, and they have a relation. So the mapping cone of the chain compress from K0, it has a distinguished map to the chain compress of the K infinity, and this this is isomorphic to the chain compress of the node 1, K1. So Khovanov kind of defined something like this. So, and then it turns out that the definition, if you consider link projection modulo Reidemeister move, then it will that functor will descend Khovanov. So to bigraded abelian group. So in particular, that means if we have a node, if we have something like this, you know, if you have something like this, then the so-called combinatoric model just means that this chain complex is obtained by taking some iterated mapping cone of all the possible resolutions. All the possible resolution, something like this. You resolve all the crossing. And something like this. You resolve all possible crossing. And then Khovanov tell you how to define all these arrows so that you really have a chain complex. And then the homology of this chain complex will be an invariant of the link. So this is what combinatoric model means. So it kind of defined by resolving all the crossings into this form, into no crossing. And then you can do similar things for annular setting, meaning that instead of considering links in S3, you consider links in R2 delete origin times R. And then you project your link to R2 delete the origin, and then do the same thing. R2 delete the origin times R is the same as S1 cross B2 topologically. And do the same thing. And that is the annular theory. Now, maybe I should have said that the annular theory is not defined by Khovanov. It is defined by these people. But the definition is really the same. It's not very different from Khovanov's definition. Now, let me explain what is a two-periodic link and what is a strongly invertible link. Yeah, any sigma will also work. There's also a theory for any sigma times R. And also you can twist the theory by something. There are always a lot of twisting information you can do. Yeah, they also have theory in sigma times R. I'm not sure whether sigma times R is also defined by these people or some other people, but there is that theory. And then, so now, two periodic link. So I will draw something like this. And let me, so this is an example. I have a Z mod 2, this is a knot projection of a link, and I have a Z mod 2 symmetry of the space, preserving the link, the Z mod 2 symmetry of R2, the obvious rotation. And then, and there is no fixed point on the link. That means the fixed axis, so this axis is fixed by the Z mod 2 action, and it doesn't intersect the link. This is what is called two periodic links. And then for two periodic links, you can take the corresponding quotient. Just rotation by 180 degrees. So in general, you can consider Z mod 2 action on S3. That's such that the fixed locus, such that the link is fixed by the Z mod 2 action, and it is disjoint from the fixed locus.
Why would you need that?
Why do I need the disjointness from the fixed?
No, the two
I want to relate. Why do I need? So the spectral sequence I want is not the spectral sequence that you are thinking. So the spectral sequence that you are thinking doesn't need that relation. And I'm talking about another spectral sequence. So quotient just means the obvious thing. Quotient just means you just chop it and then take the quotient. So it looks something like, maybe something like this. Yeah. Okay. And then a question is the Khovanov homology of this guy and the quotient, are they related? Does the quotient live in S3 as well? Yes, that's right. So for the ambient space, just try to remember. Yeah, it's also in S3 as well. It's also in S3. So you can kind of think of how should I say? So yeah, the answer is yes. So this axis is kind of fixed by the Z mod 2 action, and when you take quotient, that axis is still there, and it will give you S3. You will give you a link in S3 if you think about it.
Sure. So do you want the Z2 acts on S3?
No, not by antipodal map. Antipodal map, there is no fixed axis. I really want a map like this. Yes, that's right. Maybe it's easier to think of R3 rather than S3. Yeah, let's think of it as R3. So some answers. So Seidel-Smith in the symplectic version of Khovanov homology, they and after collapsing by grading to a single grading, so they prove that there, of course, in their theory, they only have single grading. But yeah, so the thing is, they prove that there is a spectral sequence from the Khovanov to the Khovanov of the quotient, which implies that there is a rank inequality work over characteristic 2. Z mod 2 action, so that's why I work over characteristic 2, so that my BZ2, say F2, is a polynomial ring. So anyway, I work over characteristic 2. So then there is a rank inequality. But the interesting thing is that Seidel and independently Cornish, they realize that there is no spectral sequence of this form that is compatible with the by grading. In the combinatoric model of Khovanov homology. Instead, what they have in the combinatoric model is Straffagan and Zhang. They prove that there exists a spectral sequence from the Khovanov to the annular Khovanov of the quotient that is compatible with the bigrading. So in particular, there is a rank inequality. And this is so, and in general, so some general facts. In general, there is always a spectral sequence from the annular Khovanov homology of a link to the Khovanov homology of the link by embedding S1 times D2 to S3. So, and in particular, so this is telling us that this is telling us that not only the rank of this guy is greater than this one, not only the rank of this guy is greater than this one, and not only the rank of this one is greater than that one, the rank of this one is actually greater than that one, or equal. And this has important application in low-dimensional topology. So Baldwin, Hu, and Zivik, they show that they use this rank inequality to show that the Khovanov homology actually detects the 2,5 torus knot, meaning that if you have any other lot that have the same Khovanov homology as the 2,5 torus knot, then it is the 2,5 torus knot. So, and the proof, and the way they prove it is way more complicated than it should be. So, and their proof, as proof. So, what they do and is they need to use equivariant and Khovanov homotopy type. That means from link projections. So we have a functor to chain complexes, but actually it factors through. So this is Khovanov. It actually factors through spaces, and then take homology, or take chain complex. What they do, and they need to use this. So the Khovanov homotopy type and map this link projection to actual spaces rather than to chain complexes, and then do something. This is right. This is a long story. So this is they kind of ad hocly define the spaces by and so just like those 4 homotopy type program by Cohen Jones Siegel, you really instead of using those instead of just keeping track of the generator and the index, you really keep track of the differential in higher dimensional moduli spaces. They of course they didn't face it that way, but that's the motivation or that's the moral behind it. Invariant of the link. The space itself is an invariant of the link. So it's not only the space itself. You should think of it as a space together with a equivariant space. In this case, yeah, it's an equivariant. Up to equivariant homotopy, it is well defined. Yeah, it's a long story. So I didn't read that paper. So I know the reference you should look for is Lawson, Lifshitz, and Saka. So yes, I can say a bit more in the Lagrangian flow case, but maybe not in this combinatorial. Maybe after the talk. So and then if you have some space with some Z-mod 2 action, then there is something classical called Smith theory. For Smith theory, it says something like if you have a space, if you have some Z-mod 2 action, then you can compare the chain complex of the space and the chain complex of the invariant part of the space. And then if you work over characteristic 2, then there is a spectral sequence of this form. And then they apply the Smith theory to the spaces. And so the Z-mod 2 action is obviously the Z-mod 2 action that you are thinking of. And then the next thing is what is strongly invertible? Strongly invertible knot is even more is more interesting. So strongly invertible means the following. So there is still a Z-mod 2 symmetry, But then you something like this. Something like this. So there is still a Zermot-2 symmetry, but now there are 2 points on the length. That intersects the fixed locus. The white point there and the red point there. The red point is underneath the white point. There are 2 points intersect the axis. And then you can correspondingly, so this time if you form the quotient, then it will be problematic. So we cannot just take the quotient, but we can first resolve it and then take the quotients. So we have 2 quotients. So you resolve it, meaning that you do something like replacing the blue guy by 2 blue guy. Let me draw in purple, and then replace the red guy either by this orange thing, or either by this orange or by the green. It's your choice. There are 2 different choices, and these 2 different choices will give you 2 different quotient. And the I have 2 ways to do it. Either you make it like this. This is the first way. Resolve the crossing. You resolve it.
And what happened to the original brain?
I didn't change my original brain. I just resolve it. And then I have 2 resolutions, K0 and K1. And then after resolving it, then K0 and K1 doesn't intersect the axis. And then I can take the quotient.
Sorry, the first picture is something like
the first picture is here.
In Hilbert's scheme of 3 points. The second picture is in Hilbert's.
That's right. That's right. That's right. Yes. The first picture is in Hilbert scheme of 3 points, and these 2 pictures will be in the Hilbert scheme of 2 points.
Still someone know how to.
Yeah. I still know how to do it. I will explain how to do it if I got the time. So, and then after the 2 ways of resolving, so I have done this exercise. Let me draw it here. Something like this. Go to here. And then the axis, the blue axis, you go to here. Something like this. And then the other guy is very similar. And then this. And then the blue axis is here. Okay? Now, I want to think of K as the Khovanov homology of K. But I want to think of these 2 quotients as in living inside a solid torus. I just want to use the annular theory for these 2 guys. So I want to remember this axis, the blue dot. And then you can see that if I remove the blue dot, they are the same. But if I insist that I put the blue dots there, put the quotient of the invariant axis there, then they are related by something called an axis moving map. So what I'm saying is that there is a map from the annular Khovanov homology. There's a chain map from the annular Khovanov homology of the 0th quotient to the first quotient called axis moving map. And then, so Lipschitz and Saka, they use equivariant flow homotopy to prove that there is a spectral sequence from the Khovanov of K to the cone of the axis moving map of the quotient. Let me call it F. So there is a chain map. I take the corresponding mapping cone of the chain map, and which is a chain complex, and then there is a special sequence from the Khovanov chain complex to this guy. In particular, there is a corresponding rank inequality. So they use the same method to prove it, essentially. Yes. Axis moving map, yes. Combinatorically, it is defined this way. So you draw a little circle. Let me give myself more space. You draw a little circle over there, and then you do cobordism. So in their theory, they have cobordism map. So what you do is you kind of link the two things. You kind of resolve along this circle, and then if you open up, then you will get that.
So is that group point an actual point or just a mark point?
It's a mark point. It's the axis. So it's the axis used to define the annular Khovanov homology. The blue point is the annular axis. Is that blue point is exactly the same blue point. This is an annular axis. The annular axis is the fixed locus of the Z2 action. Let me go back to my original picture.
Are you going to have some relation between this the final homology with the one where you delete the blue point?
Delete the blue point? No, not quite. Not quite. So what they did is they applied this for homotopy type, Khovanov homotopy type to get a space, and in the fixed locus of the space, they realized the fixed locus is topologically the mapping cone of this map, which is kind of amazing. And then, okay, and I'm going to explain. So they really analyze the fixed locus of the Khovanov homotopy type of this link. Understand the fixed locus, and the fixed locus is exactly the homotopy type is exactly the mapping cone of that map. No. Equivariant Khovanov homotopy type is done by these people, and that spectral sequence is done by Lipschitz and Saka. And then, okay, I'm going to tell you symplectically how to understand these spectral sequences. So, how much time do I have? Okay. So, the theorem is that there are symplectic analog of this spectral sequence. And so I need to quickly recall the symplectic model, and then I will explain how to get this. Symplectic model. So we start with 2m pairwise disjoint points on C, point in the configuration space of C. Let me call them T1 up to T2m. Associated to such a data, I consider the corresponding hypersurface in C to the 3. And then from there, this guy comes with a map. by projecting UVZ to the Z coordinate. And the critical values of map pi are precisely all the T1 up to T2M. And then, so this is my C, and then I have my T1 up to, so this is a T1, T2, T3, T4. You can think of this as the base of my vibration at pi. And then I draw some circles. So I have this, not circle, I draw some arcs connecting them. I have this blue collection, and I have some red collection. I have some red collection as well, something like this. The blue collection will give us a Lagrangian, give us a blue Lagrangian inside something called the horizontal Hilbert scheme of this A tau. So Hilbert scheme of 2m points of A tau, and then you delete something. So I will not explain what I delete. If this is if you see this for the first time, just regard it as the Hilbert scheme. And then the red collection also will give us a Lagrangian inside. And the symplectic Khovanov homology, the symplectic version of this link. Let me draw one that actually has a crossing. Let me draw something like this. Then is the symplectic Khovanov homology of the link obtained by regarding the blue guy is higher than the red guy. Is so something like this. Is the Lagrangian flow cohomology between K and L up to gradient shift. So you turn a link, you turn a knot projection of a link into two Lagrangians, K and L, in some space, and then compute the Lagrangian flow cohomology. So this space has different descriptions. So if you are a physicist, then maybe you might like to think of this as a Coulomb branch. I don't know. So some Coulomb branch. And you can also do something similar using A star tau. Inside C square UV cross C star Z. Inside, if you take the hypersurface inside here instead, then you can define an annular link invariance in exactly the same way. And this is, in my talk, this is my definition of annular symplectic Khovanov homology. So now, there is a theory for Lagrangian flow cohomology. There is a corresponding Smith theory. So that means if we have some symplectic manifold, Lagrangian submanifold L0, L1, and with a Z-mod 2 action, preserving all of them as a set, then to together with some additional technical assumption about the together with some technical assumption, then there is a spectral sequence of the form of L0, L1 taking flow chain complex in M to the invariant part. The Lagrangian flow of the invariant Lagrangian, the invariant parts of the Lagrangian, and take the Lagrangian flow in the invariant parts of M. So there is this is the Lagrangian flow analog of Smith theory. And we want to use that to understand the spectral sequences for two periodic links and strongly invertible links.
So, I mean,
yes.
the starting point is clear what to do. And on the maps, you just draw all the maps that are non-invariant.
Yes, so yes, the spectral sequence is defined as follows. So, so first of all, you do equivariant, Borel equivariant Lagrangian flow theory, meaning you do everything over. So you take M cross EZ2, mod Z2, and you do flow theory in family over BZ2. You get this? And then this guy will be a module over BZ2. And then it's just like usual localization theory. And this has a F2 theta module map to the fixed locus. And this map is obtained by under some technical assumption. You can put this complex inside here, kind of, and then so in Morse theory, it is just really pull back. You put the fixed locus here and take pull back, and then this map will become an isomorphism if you invert the generator of the if you invert the equivariant generator. So theta is the generator of BZ2. That will become an isomorphism, and this guy is related to this one by a tautological long excess sequence, and that tautological long excess sequence means that we have this we have a long excess sequence of this form, and then this together with this map will give you this spectral sequence. So equivariant localization together with this in the so did I answer your question, or should I say something more here or there? So you really use the Borel equivariant flow theory. You do flow theory over the Borel space, and then together with some structural result that you can see, which gives you some algebraic properties. Yeah, I guess this way of saying is a bit too vague. Where should I explain more?
If I know my original flow theory,
yes.
Assuming that L0 and L1 are spectral equivariant.
Yes.
Do you know the other one as well? Like, do you have to do some hard work, or
this one?
Or it's just happening?
So.
I just want to get a feel for how.
So yeah, so let me say some word about this. What is this? So So what you do is you have your BZ2 here, and then you choose a Morse function, and then you have so many critical points, and then over each critical point, you do a corresponding flow theory. So generators of this complex is a tuple. The first entry is a critical point of a Morse function of BZ2. The second entry is a generator of the flow complex over that critical point. And then when you count differential, you count coupled equation, you count gradient trajectory together with the corresponding, together with a flow equation, so together with a solution of the flow equation lying above this gradient trajectory. And that defines the differential. So if you just know, what should I say? So it has more data than just the chain complex itself, together maybe with a naive Z-mod 2 action on the chain complex. It has more data than that.
So in the case for BZ2,
yes.
the critical points was
The critical, this is just RP infinity. And then the critical point, there is one critical point for each non-negative degree. And there are two rigid gradient trajectory between consecutive degrees. And of course, they cancel out. But there are also some higher dimensional cells of gradient trajectory between critical points of index bigger. And then you need to take into consideration of those as well, because it is possible that you have some gradient trajectory which lies in a higher dimensional moduli space, which couple with some flow solution on top, which make it rigid.
Yeah. So how do you? Okay, maybe I need to read it.
Yes, I can. There are lots of references. So the Seidel-Smith, of course, in the original paper, they consider involution and localization. They have this, and then for Z-mod 2, and then Onstra, maybe together with some people, they do a S1 equivariant version. And then there are also some Z-mod 2 version by they are doing Borel equivariant flow for different purposes. So that's why they have different settings. And I actually also, just to kind of advertisement, I also have a work which consider BG. And G is a compact Lie group. And in that case, we show that there is a Coulomb branch action on the symplectic homology, G equivariant symplectic homology of something. And depends on whether M is a Liouville manifold or whether M is a closed manifold. In the closed manifold, you should replace it by G equivariant quantum cohomology. And when M is a closed manifold, then so the support of that will be a Lagrangian subvariety of the spec of the Coulomb branch algebra. But anyway, so just to say that even for compact Lie group, I also have a paper writing something like this.
Yeah, maybe you could tell us later about this.
Yeah, okay, yes. Okay. And then I want to talk about how to see the spectral sequences. The goal is to use this theory. Lagrangian Smith theory. get the spectral sequences that is analogous to the combinatoric model. So let's do the, so, right. Okay, so I said that the symplectic manifold is a Hilbert, roughly speaking, is the Hilbert scheme. So in an open chart, there is an open dense set, which just correspond to having pairwise disjoint entries. Roughly speaking, you need to delete something, but let me just say that. So disjoint entries. So now I have I from 1 to 4m. Let me just say in this way. I have now my base. I have 4m points in C because I'm considering the two periodic case. So I'm considering two periodic case. So I have 2m many here, and then another 2m many there. And then I have some two periodic thing happening. So this is my link. And then, so the fixed point, so I consider the involution where I send ui, vi, zi to minus ui, minus vi, minus zi. I consider this involution on my space. And then the fixed locus are precisely ui, vi, zi, and minus ui, minus vi, minus zi, I from 1 to 2m. You are right, it doesn't preserve the mass of grading. But still, yeah, so even though it doesn't preserve the mass of grading, there is still such a spectral sequence. And then this fixed locus, I can identify, I can define a map from this fixed locus to ui, zi, vi, zi inverse, zi square, I from 1 to 2m. This is well defined because if I pick this one, minus times minus is positive. So from this guy to that guy, it is well defined. If I just take ui, vi here, it is not well defined. And then it turns out that this map identifies the fixed set for m pi a tau fixed set with the help 2m pi a tau square. Tau square means I just square entry-wise, just take square. So tau itself is fixed by a ZMO2 action. So tau itself is something like plus minus T1 up to plus minus T2m. It's something fixed by the ZMO2 action. Sorry, there's a star here. The fixed locus, so this is Khovanov story, but the fixed locus land in the annular Khovanov. The fixed locus doesn't have things lying above the axis, lying above origin. And then essentially the spectral sequence just boils down to this fact together with the fixed locus under this map will correspond to the, I don't know, the corresponding Lagrangian for the quotient nodes. and then apply the Lagrangian-Smith theory.
So how do you compute this?
Just compute it, really, literally, just compute it. So
how do I see it?
So the reason is, okay, if you have some point over the origin, okay, if Zi is 0, this is 0, then UIVI and minus UIVI, they are different points over the origin. So it got deleted by horizontal Hilbert scheme.
So the equation there is like
None of the Ti is 0 because I'm considering two periodic case. So there is no, tau is not 0 here. So in the two periodic case, I pick 2. So I'm literally taking that. So this is T1, T2 up to T2m, and this is minus T1 minus T2 up to minus T2m. I'm considering 4 endpoints on C. They are not 0. And that's why the fiber over the origin is an actual smooth fiber, is an annulus. And the negation action on the annulus has no fixed point. So that's why it lands in the annular theory. Okay. And then the more interesting thing is about this strongly invertible case. So what happens to the strongly invertible case? Strongly invertible just means that the knot looks like this. It passes through the origin in a particular way. Only each collection only intersects the axis at one point. So something like this. Something like this. So the right collection intersects the axis at one point, the red collection intersects the axis at one point. That is strongly invertible. Okay, so now again, just do the same thing. And this time, maybe I should have remarked that. So remark. So in the above, if we use the involution UIVIZI goes to UIVI minus ZI, the fixed locus will be this with the actual A here, not A star. And this is how Seidel and Smith got the spectral sequence from Khovanov to Khovanov. That doesn't preserve by grading. But it's not compatible with by grading. So the moral of the story is that the correct involution that we should take is that one, that slightly less trivial one than this obvious one.
Oh, so actually, in your case, because it's annular,
yes,
it does preserve the grading because the homologic form is easy over
yeah,
here.
exactly.
So it will preserve it here.
Exactly.
Yeah.
Exactly. Okay, now from even number to odd number, it suggests that the involution we use in the strongly invertible case is this one. Okay, so use this involution for the strongly invertible case. No, it will, wait, it will preserve this yeah, I mean you can work out what you will try to work out. So but now I want to use these involutions for the strongly invertible case. So it means what? So if I have something that is fixed locus in in an open dense set, the fixed locus will be of the form of ui vi zi, ui vi minus zi, dot, 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 dot. And then there is an extra one, which is lying over the origin, because I need it to be fixed. So all the other, they pair with each other, but there is one that is lying over the origin, which doesn't pair to anyone. So that means, for example, let me draw a simpler situation. Let me draw something simple.
Sorry, what do you mean the delta fixed locus? You need to build back from one variance there?
So now I consider Hill of 4m minus 2 a tau, and with a pi, and then I consider this set mod 2 action on here, and then the fixed locus. So points in here are 4m minus 2 many points in a tau, and then I will have 2m minus 1 pairs, which are related by just changing zi to minus zi. And then I will have an additional one. Wait, did I make some? 1, 2, 3. So 3, I need 1, 2. So 4m minus 2. Divided by 2m minus. Yeah, that's right. So so what am I? No, what am I doing? So this is 2m minus 1, but tau is inside configuration of 4m minus 2. Yeah, that's what I mean, sorry. So, so that means this is m minus 1 pairs. And then I have one additional point. Yeah, sorry, that's what I mean. So the tau is in this configuration space, but the corresponding Hilbert scheme I take is this Hilbert scheme. So I have an odd number of points in a tau. One of them kind of special, lying over the origin. The other points, they pair with each other, pair up with something. So let me draw an example. Very simple example. So in this case, so Lagrangian flow cohomology is categorizing the intersection number. So I want to look at the intersection between these Lagrangians, which are generators of the flow complex. And in this case, there are some generators of this form. And yeah, I didn't say it, but actually this guy corresponds to 1 point, but in the middle there are 2 points lying above here. Because my, yeah, I didn't introduce that. Yeah, they are circles, yes. So, and now, if you stare at it, and then you will realize that, let me call these 2 points A and B. A pair with these two. Do not talk to B pair with these two at all. In the sense that, in the following sense. So, okay. So let me define the map first. So I can define this to ui vi zi squared. And it gives us a fiber bundle of fixed and -1. It gives us a fiber bundle with fiber being T star S1, which is the fiber over the origin. So because this map is forgetting this data, and this data is precisely the T star S1, the fiber over the origin. And then I have my L0 fixed here and L1 fixed here. And this map, they will map to something. So, okay, let me just draw pictures, and then and then I will conclude my talk. So, the corresponding two quotients of this guy will look like and then an annular axis here. And then I have my green point. My green point. And some other point, let me call it orange point. Yeah, there is an axis moving map. So in symplectic world, the axis moving map is just a continuation map. You just really literally move the point to there. So you fill in the puncture, and then you move the point there, and use the annular axis to define a filtration, and you will have a filtered continuation map. And that is the axis moving map. And then the point is that the orange guy, the blue guy will define a quotient complex, and the orange guy no, the blue guy will define a subcomplex in this case. No, the green one will define a subcomplex in this case. But then is a right, who is the green one? The green one, right. So there is a correspondence between this picture and that picture. So if you forget this half, if you forget this half. This green is literally this green. You just remember all the generators that you can see in the fixed set, which in particular has one point over here, over the axis. And then the axis is actually very close to that point. When you resolve it, you will see an intersection point over there. The axis is very close to that point. And these green dots really correspond to those green dots. And then the orange dots, you cannot see the orange dot upstairs because the orange dot upstairs will correspond to something like this. It has no point lying over the fiber over origin. And there are four of them. There's always even number of them. So you cannot see the orange point upstairs. The orange points, they don't define intersection points up there. But in downstairs, in here, you will see the orange points. And then the axis moving map. And it turns out that because of the position of the annular axis, in the annular theory, the flow differential can only go one way. And if you put the axis out, the flow differential can only go this way. If you put the axis in, the flow differential can only go this way. And the axis moving map, F, is the identity here. And when you restrict to N, but when you restrict to C, it is 0. So the cone of AKH.
Are you imagining the floor differential to go in complement of it? Like, should I think of it as a bit of a picture? Why do you say the floor differential goes one or the other way?
Because so the flow differential, you have this annular picture when you project it. So whether the projection hits the annular axis or not, right? So by open mapping theorem, so if the corner looks like this, then it can only be an output if there is an axis there. If the corner looks like this, then you can only receive flow differential from outside in this picture. And here you can only receive flow differential from inside. And that will tell you whether it is input or output. So the whole plane happens on C minus the blue dots. Yeah. In this picture, there's not even differential outside because this picture is too simple. But I can draw more complicated picture, and then there will be there. Yeah. Yeah. Sorry for the confusion. Yes.
So the axis changing map.
Yeah.
Is a map between your complex as well. Why is it that you said it is a continuation map?
Yes, a filter continuation.
How can I see that?
Right. So this is this annular picture. If I add the axis in, then I can define a filter chain complex filtered by how many times it hits the axis. So I can have a chain complex over something, I don't know, some Q, something like this. And then, so AKH is the same as setting Q equal to 0, meaning that you don't look at anything that passes through the axis. Q is equal to 0 means the intersection with the axis is 0. And so there is a map from here to there as F2Q module. And you have two specialization giving you two annular theory. But so this filtered continuation, map, CH1 to CH2 from this chain complex to that chain complex, it will act as the identity on this generator N. but it will act as Q times something on the for the generators in C. But when you specialize to Q equal to 0, this is gone. And so this is what the axis moving map is doing in the symplectic story. Did I answer your question?
For me, I still have difficulty recognizing the continuation.
So the continuation map is the following. If you fill in the puncture, then you can move this red dot. You can move the red path to that one, and this family of Lagrangian this family of path will define a continuation map from before and after. The one to the one wrap more. I what do you mean wrapping more? I'm literally just moving the Lagrangian across the blue dots. Yes. That is the continuation map. And then yeah. But this continuation map, anyway, so we have this continuation map. And this continuation map turns out to not giving you a Cauchy isomorphism over F2Q, because if you do the continuation backward, if you invert Q, then you will get a Cauchy isomorphism. But if you don't invert Q, it doesn't give you Cauchy isomorphism. But this the total chain complex of this is the same as the homology of C 2 times, because this is quotient complex that is Cauchy isomorphic to C. So you have 1 copy, 2 copy, which matches well with exactly this picture. So I have 2 copies of green generators because I have 2 points over the origin, and they don't talk to each other. You can check that in the fixed set. In the fixed set, the flow differential doesn't allow them to talk to each other. And this is the proof. Okay, that's all for my talk.
Do you have any generalization
to right, so that's a very good question. So there is some additional assumption here that I didn't say. And in FP, it is it's actually very technical, and there is no such theory in the literature yet for FP. It is actually significantly more difficult than SEMO2, surprisingly.
But there's no obvious reason.
Yes, there is no obvious. But of course, you need to put the right additional assumptions. So, but if you think of flow theory as flow homotopy type, you really map to spaces. Then there is no reason that it will fail. But you just need to do it carefully.
Also, this flow theory in F2.
Yes. The localization theory is just doesn't behave well, I guess. So you can see from some example, right? Let me try to see. Yeah, I guess even for the original Smith theory in the classical topology, you don't work. I think people, if you want to get a rank inequality, something like this, then you don't want to work with things that. Yeah, I don't really look into that.
So you said that this simplified relationship is another proof.
Because our proof is if you already know Khovanov symplectic Khovanov homology, our proof is really very short. Their proof is quite long because they need to.
Can you summarize how you would do it?
I summarize is just compute a fixed set, and then which is I think not too difficult to compute. And then in the two periodic case, that's essentially done. You compute a fixed set, the Lagrangian correspond to each other, and then it's just a Lagrangian Smith theory, and then that's done.
You're trying to prove that Khovanov homology detects the 2.5.
No. I'm not doing that. I am saying that there is an application of this rank inequality by others. I'm not proving that.
Oh, I see. Okay.
I'm not proving that.
I see. So you're just proving the spectral sequences.
Yeah, I'm just proving the spectral sequences. I'm just proving. Yes.
Can you remind us then again, how does the spectral sequence arise now? Because usually you get a spectral sequence from a double complex, or
right. So yes. So where is it? No, here. So this is we have this module map, and this module map becomes an isomorphism after localization, after inverting theta inverse, after inverting theta. Becomes an isomorphism. So, and then now that means I want to compare. That means I want to compare this one with I want to compare this one with this one. This one with this one.
But neither of the original Khovanov homology. Homology would be Khovanov.
This is this. So just tensor. This is naive tensor. Yeah, this is naive tensor. Naive tensor product.
With the same differentials before the tensor.
Yes. This is naive tensor product.
Okay.
And then and yeah, to be more precise, I both of this and that I should take tensor with a naively tensor with that. Let me write like this. This is the precise statement should really be that with tensor and then spectral sequence. And then now this is really this is as I said in this localization theorem, this is really the same as the naive tensor product. And then to get a spectral sequence from this to this, observe that there is a theta map. There's a theta map which define a filtration on this guy, and then the the E1 page of that theta map. So this theta map, the E1 page of that theta map is precisely, yeah, I mean, let me write like this. Let me write on the chain level. It's really something like this. There is a source exact sequence of this. Is it? Yeah, that's right. And then you can think of this theta give you the filtration. And then that filtration gives you the spectral sequence where the E1 page is this. And then the final page is that. Yeah, I'm
missing some of the abstract theory here. Do we get a spectral sequence of Lur complexes from a broad exact sequence of underground, or do we get a, or do we just have a filtration on the complex? Like that, the filtration gives us the spectral sequence.
So we have we say it again. So we
Yeah.
Yeah.
Let's see. So a filter chain complex with an additional filtration gives you a spectral sequence.
Yes, that's right.
And, but it's not necessary that it converges.
Yeah, it converge. It converge. In this case, they converge. They converge.
Why, for example?
Finiteness, because of everything is compact. There is no way it's not. It doesn't converge.
Why does it converge to the right thing?
Because because it is really a bounded complex. So I mean what should I say? So because the cohomology of this after inverting theta inverse is really the right thing. The cohomology of that.
So you have this short line sequence, so equivariant over complex. The first two terms are equivariant over complex.
Right. So you can think in this way. So that equivariant flow theory is lying over the Borel space.
Right, I understand from that.
Yes. Yes.
But I don't understand
this. Theta is going the. I guess. So.
Recording stopped.
Yeah.